A couple of schedule-related things. First of all, class on Friday of this week is just going to be a recorded lecture video. And then Monday of next week, we're going to have our first midterm exam. So I'll give you some additional information about that first exam here on the next slide. But aside from Friday of this week, it's also going to be a recorded lecture video for Friday the 16th of February and Monday, March 25th. So I wanted to let you know in advance in case that affects anything you do scheduling-wise when it comes to work or childcare or anything else. I've just loaded another homework assignment onto Blackboard. It's got 3 problems related to groundwater. We'll get into the problem-solving part of the groundwater topic in class on Wednesday. So you'll have Wednesday till Monday to finish those 3 problems. And then the exam on Monday, our first midterm exam. So let me tell you a little bit about how we're going to do that. We've got 50 minutes for the test, and it's going to be a mix of both concept questions and problem solving. Some of the concept questions are going to be related to things that we've talked about in the lecture. I may also ask you to just define some terms. And you'll remember I handed out a page full of lots of terminology. And so what you should do is go through that for the chapters that we've covered so far, up to and including the groundwater chapter, which is in chapter 6 of our book, which we're starting on today. So I haven't written a test yet, but my intention is for maybe about 1/3 of the points to come from conceptual type questions, maybe a little bit more, but you know, the majority of it be problem solving, but a significant amount of the points and the value on the exam will just be related to your understanding of concepts and terms and the fundamentals of the hydrology science that we've talked about. You should bring your laptop because some of the problem solving you may be asked to do during the exam could be related to Excel. So if you think about how we've used Excel so far this semester, one thing that comes to mind is the assignment you just did where you're using Excel to solve for infiltration rate. You can also prepare a page of equations, and you can't just put all the terminology that you're supposed to learn for the test on there. It should not be a concept sheet, it should be an equation sheet. So you can define terms like variables, you know, so for example you could remind yourself that capital F of T is infiltration depth. You could also include the units, so you could say infiltration depth cm. You know, if you had the formula above that, you can define the terms on the equation, but you can't just have like a short description of what causes precipitation. You can't have a reminder of what's the difference between orographic lifting and convective lifting versus frontal lifting. That's supposed to be in your mind. So when you prepare that equation sheet, please put your name on it because I intend to collect it with the exams, and I'll look over that just to make sure that it's just equations and not conceptual details. So I regret we don't have more time than 50 minutes. It would be more fun if we had longer time for the exam, but I'll do my best to make it so that most people finish with plenty of time. That's always my goal is, you know, if it's a 50-minute exam, probably the first person will finish in 25. Most people will be done by 40 minutes, and it'll just be the stragglers at the end who, like myself, I like to take really long exams. When I was in school, we had a testing center. We didn't take exams in class. The exams were on file for like a 24-hour period in a section of the library, and you could just go over there and take as long as you want in some cases. I once took a calculus test, and I was in there for 5 hours. And I didn't need 5 hours. I just took a break in the middle of the test and ate some candy and rested my brain and started back up later. So I'm a slow test taker, and that's why I try to be sympathetic and not making these too long or time pressed. But what I realize is if you don't know the material, then no amount of time is really going to feel like it's enough. So anyways, any questions about the exam or how that's going to be formatted? All right. Well, if not, did you have your hand raised? Oh, okay. An infiltrometer is a way to do a field test related to infiltration rate. And this is a single ring infiltrometer. And what you can see is that they put a certain amount of water in a pan that's open at the bottom. And because it's open at the bottom, then the water is going to penetrate through the soil. And you can see that there's a ruler in there. They would mark the amount of time that it takes to fall a certain distance. And so the disadvantage of a single ring infiltrometer is that not only are you getting some of the water going downward, but it's also spreading sideways. And so this isn't a good indicator of the rate of infiltration that would occur during a rainstorm, because in a rainstorm you'd have water falling over a large area, and the sideways movement of water at the fringe would be negligible compared to the downward rate. And so the way around this, if we want to do like a field test of potential infiltration rate, is a double ring infiltrometer, where the outer ring is going to provide the amount of water that is satisfying the sideways movement of water in the subsurface. And so you can see that it's penetrating sideways because of the outer ring, but then the water level that's falling in the center ring is just related to the downward penetration rate of the water. So it's going to include both gravitational effects and also the suction effects. And there is some amount of downward pressure because of hydrostatics, but usually they would only have a couple of inches of water, and so it's not a great amount of excess pressure forcing water into the soil pores because of the pressure at the bottom of the ring. It's just mainly going to be a function of the soil characteristics and the moisture content in the soil when the test is being performed. And so they have calibrated this test over lots of different soil conditions, and they know what it means when the water depth falls a certain distance in a certain amount of time. And they can relate that to hydraulic conductivity, moisture content, and so on. When we talk about the subsurface, I've already talked about a little bit about what porosity is, and remember that there are three things underground. There are the soil particles, there is water acting on the outside of the soil particles, and then there is a void that has air in it. And if the void is completely filled with water, then that means it's fully saturated, and I guess we'd say it's not really necessarily a void if it has the water in it. But the porosity is the volume of the voids to the total volume, and that's the voids that aren't the solid materials. And a typical range is from 25 to 40% of the unit volume in a subsurface environment is voids. And we define the soil moisture content is the volume of water to the total volume. And so typically the soil moisture content, that's my email noises. Let me just close that. Now we won't have to listen to it. Sometimes I feel like my job is deleting email because I get so many useless, I'm sure you do too, right? Like everybody just thinks that sending another email is going to solve the world's problems. Man, oh man, I get so much email. Like probably 200 messages a day. Yeah, it's bad. Soil moisture content will never be higher than porosity because porosity is like the maximum amount of empty space, and so porosity is the upper limit to the soil moisture content. If we think that all of the volume that is voids is full of water, then for fully saturated, then porosity and soil moisture content are equal. So the soil moisture content can go from 0 if the soil is dried in a heater, all the way up to porosity. During a storm, when the wetting front is moving as a wave downward through the soil, then the moisture content increases in the amount of delta theta. So it's going from the initial water content to saturated. So that's the increase in the water content is the delta theta. And then after it's drained by gravity, we say theta sub r is the residual moisture content. So that's not that it's been air dried and like the soil's been removed from its original environment, spread out and air dried, that wouldn't be residual. And it certainly doesn't mean that it's been kiln dried or dried in a heater. It's just residual moisture content is in the field after it's drained by gravity. So sometimes we'll have to calculate the effective saturation of the soil, and what we can think in the numerator is the available moisture at a given moment in time. So it could be sometime after the storm when the soil is not fully saturated but not fully dried out, and in the denominator is the effective porosity. So we've talked about Darcy's law a little bit, just in basic terms so far. This diagram shows it in a way that I've seen in a lot of texts, and frankly I think that this diagram makes it a little bit more confusing because the gravitational effects are harder to discern when the soil column is up and down. Like the way that I've showed you in a previous class meeting is I've showed the soil column on its side like this. And it's the same equation whether the soil column is on its side or whether it's vertically oriented. So let's just look at it vertically oriented because you're likely to see a diagram like this again in the future. What this is showing is that we have a constant head, both the water coming in to the soil column and the water going out is at a constant head. So that means that we're equilibrium with the flow rate that's going through here, and it's equilibrium in terms of the head values. So there's a certain amount of water pressure for the water that's in the soil, and a different water pressure at the bottom of the column or at the end of it. If you think about the water is traveling in a certain direction from the top of the column to the bottom of the column. This difference in head, if the water wasn't flowing, then the piezometer would rise to the same level. So if there was zero flow rate, so if we could put just, there's sand in here but an impermeable barrier at the bottom, like a clay plug or a piece of plastic, so that the water isn't flowing through it, then this piezometer, which measures the pressure, would rise to the same height. So the difference in the head values is because of frictional effects as the water is flowing through the soil. The water is flowing through tiny little spaces, and there's a lot of energy loss as the water flows through a small diameter environment to get from one point to the other. So the difference in head between the upstream and the downstream location in the soil column is what's driving the flow. And we have constant water surface elevations just for ease of knowing that this is in a stable equilibrium. So Darcy's law says that there's a proportionality factor K, the hydraulic conductivity, that relates to the flow rate of water that's going to be able to make it through under some driving force. And the driving force is the difference in heads divided by the length. And then the area that the water is flowing through is not just the void area, it's the entire area of the soil cross section. So in the case of a cylindrical column, you'd need to know the diameter of that column, and then you'd be able to calculate the area. If it's a rectangular column, you just multiply the length by the width, but it's the flow area that the water is perpendicular to as it's going down through the column. So Darcy's key insight was that there's this constant that relates to the soil properties, and that tells you the rate of water that can come through the soil, and as units of length per time. And so sometimes you'll see hydraulic conductivity expressed in meters per day. It could be centimeters per second. There's a wide range of units that are used for hydraulic conductivity, and a really wide range of values depending on whether you're talking about gravel at one end of the spectrum or clay at the other. You could be talking about like 1,000,000 times the hydraulic conductivity from one soil to the other. Sometimes we would combine the head to length ratio and just say that that's J would be the driving force. And so if we're thinking about an analogy to pipe hydraulics, that would be like the slope of the energy grade line, J. And lowercase q is a flux. It's a flow per unit area. So Darcy's flux says that if we multiply the hydraulic conductivity by this pressure gradient, then that would give us the flow per unit area. So the flow per unit area would then allow us to multiply by any cross-sectional area. And so this Darcy flux is just more of a generalizable factor that would be independent of the cross-sectional area. A flux is just some amount per unit of space or area. So this is that same diagram but turned on its side, and in my experience turning the column on its side is sometimes less confusing because then you don't have to worry about the issue of gravitational effects, because it's not immediately obvious in this case that the reason why the water doesn't rise to the same level is because the soil itself is lower. But water pressure increases as you go down through a fluid, even if it's a fluid in between soil grains. And so the pressure is increasing as you go down through the fluid, but the reason why the liquid level rises to less of a height at location 2 is because of the energy loss as the water travels through there. So the difference in the water elevation isn't because of the elevation difference, it's because of the energy difference. And so that's the definition of a piezometer. The piezometer is measuring the effect of energy losses, not necessarily just reflecting the hydrostatic effect. So here, when it's on its side, we know that the pressure difference from one location to the other is negligible if it's horizontally oriented. So it's more immediately obvious that delta H is because of energy loss. Here, delta H is because of energy loss, but maybe sometimes people don't see it as quickly. So Darcy's law says that the difference in head divided by the length, if we multiply it by the cross-sectional area, and then this proportionality factor, hydraulic conductivity, then it will tell us how much water can be expected to flow through that soil column. So let's practice this. Let's say that we have a fine sand, and fine is talking about the grain diameter. So if it had a hydraulic conductivity of 3 meters per day, then what flow rate would we expect if this is a 1 meter long column? So that's the L value. The diameter is 25 centimeters. So with the diameter of 25 centimeters, you'll be able to calculate A. And then the delta H is 0.35 millimeters. So that's what's driving the water through there, is the fact that there's more water pressure at one side of the column than the other. So calculate Q. Okay, so I've written on the whiteboard here that the cross-sectional area is 0.04909 square meters, and the delta H is 0.035 meters. So then if we multiply the 3 meters per day hydraulic conductivity by the cross-sectional area of 0.04909 square meters, and then 0.035 meters of head differential divided by 1 meter of length, then that gives us 0.00515 cubic meters per day. And then if you multiply that by 1,000, that means 5.15 liters per day of water is going to pass through that. Now that is going to be the flow rate as long as the delta H is 35 millimeters. If we had it like one tank connected to another, and if the water level was falling, then the flow rate would decrease. And so that's, in this example, why they show this as a constant water surface elevation, is if you have a falling head, then the driving force is decreasing, and we wouldn't necessarily be able to say over an entire one-day period that it's 5.15 liters. It would be less than 5.15 liters if the head is constantly falling. But at the moment in time when these conditions are as described, then that will be the flow rate. And that reminds me of something I wanted to say about the homework. So any questions about the Darcy example? All right. All right, I'm sure glad I thought about this on the homework. So yesterday, this is just a made-up example, but yesterday I did a 3-hour road trip, okay? And during that 3-hour road trip, I went in the first hour 60 miles per hour, and then the second hour I went 70 miles per hour. And then in the third hour, I went 80 miles per hour. Okay, so it was a 3-hour road trip, and those were my speeds during the road trip. So 60 plus 70 plus 80 is 210. So it was 3 hours, miles per hour, times 3 hours. I went, oh my, okay, here we go. I went 630 miles in those 3 hours. Right? No? No? But I mean, you add it up, multiply it by 3. I went 630 miles because I went 60 and 70 and 80. You add it together, and then you multiply it by 3, and that tells you how many miles. Okay, so that's obviously wrong. I mean, we can think maybe more, it's less abstract than evaporation, because a lot of people, I'm only about maybe halfway through grading the evaporation assignment, a lot of people were saying, oh, actually it gets worse than this. Because I went 630 miles, but that was just in 3 hours, and there's 24 hours in a day. So how much did I actually drive yesterday? It was 630 miles multiplied by 24 divided by 3. So I actually went, divided by 3, I went 5,040 miles yesterday. Okay, because there's 24 hours in a day. So that was quite a road trip. But okay, so the reason I bring it up, let me show you the solution to the homework assignment, the evaporation one. And I mean, so far about half the assignments I've graded so far made this mistake. And so I think it's something that a lot of people had the same idea about. Here it is. Here's the evaporation model. All right. So this looks familiar, right? The data that you got. By the way, you downloaded the data as a CSV, which is like a comma delimited file. If you don't save it as a .xls file, then your formulas get lost. It only saves like the numbers themselves. So don't save it as a CSV, even though you got the data as a CSV. You need to do save as, and then change the file type to the Excel workbook, because if you save it as CSV, all your formulas go out the window. All right, but that's not the main thing. The main thing, all right, so here's the radiation, here's the evaporation rate. This is the evaporation rate during a 1-hour period. And so to find, if this is, you can think of this as like the speed. So 60 miles an hour during a 1-hour period. So the amount of miles that I drove in that 1 hour was 60. So if the evaporation rate is like 1.3 times 10 to the 7th, to find the amount, and that's meters per second, to find the amount of evaporation, you'd multiply that by 3,600 seconds, because that's how many seconds there are in a 1-hour increment, and then multiplying it by 1,000 converts it from meters to millimeters. So then at the end, what we do is we add up all of the evaporation that happened for each of the 1-hour increments. And so the thing is, you don't add the speed, you add the distance. And then that's how you find out the total evaporation in the day. And then, so that's like one of the errors, is that people were adding together the speed instead of adding the distance. And then the other error is if you found like the speed that the evaporation only applies during the daytime hours when there's sun in this model. Like this model is ignoring evaporation due to aerodynamic effects. This is just the energy method. And so according to this model, there is no evaporation at nighttime. And so you wouldn't take these evaporation speeds that occurred during the day and extrapolate it to the nighttime hours. So those were the two main mistakes that I've seen so far in the evaporation homework. Now, like, why was it so different? Because if you look it up off of the table, it was saying that the monthly evaporation was, what, 11.2 inches? And this model says it's only going to be about 4.4 inches. That's because this model is ignoring the fact that it's really low humidity. It's ignoring the fact that there is evaporation at night. This is saying that there's only evaporation during the day. And then a lot of people did catch on to, this is just one day out of a whole month. So it could have been that conditions were, maybe the solar radiation was even more intense on other days of the month. Or maybe this had some partly cloudy conditions and later on didn't. So it's partly about one day versus a whole month. But it's also that, like, we were just only applying the energy balance method here. And, you know, if you spill water at night, it will evaporate, even though the sun isn't out. So, all right. I just thought it would be simpler for me to show the solution in a group environment so that I could make that point about adding speed versus about adding depth. Any questions before we move on? All right. So remember that at the water table, all of the voids are full of water, so it's saturated. But then you can go up above the water table in what's called the capillary fringe. And even though it's not completely saturated in the capillary fringe, it may have more water than if you go further up, because the soil is drawing water above the water table due to the suction effect and because of the distribution of really small diameter voids. And then as it rains at the surface, there's a wetting front that initially it's fully saturated only at the surface, but then over time it's fully saturated at a greater depth. And so the wetting front is going downward. This is the real curve of the wetting front. The green amped method is assuming that it goes from its typical water content to fully saturated as a binary wave. But because of the fact that the suction is being satisfied as water moves down through the soil, the infiltration rate's decreasing with time. And that's what both of our models were designed to calculate, is both in the case of the Horton model and green amped, the infiltration rate should go down compared to the initial infiltration rate. Okay, so groundwater hydrology, we're going to spend the next couple of class periods talking about subsurface flow, and it could very easily be an entire course on its own. It's the study of water under the surface, both the amount, the quality, the things that cause the movement of the water underground. And just like there are computer programs that we're going to be using to simulate watershed flow, there are also a lot of really great and interesting software packages that will allow you to calculate the flow of water through aquifers. And some of the issues that are related to subsurface hydrology have to do with the movement of pollution underground. For example, back in World War II, when they were really rushing to make explosives, there were a lot of places in the United States where they would dump chemical residue just onto the soil. They called it land application. And now, decades later, that contamination is still there, and where they are trying to use the groundwater for drinking purposes, they have to filter it through activated carbon or other ways to remove the contaminants. The lowering of groundwater tables is a big issue in hydrology because there are a lot of places across the world where they're using more water out of the aquifer than is getting recharged over time. And we'll look at a video that talks about that in just a minute, the issue of depletion of subsurface aquifers. So we've already talked a little bit about the amount of water in the world, and that most of the water in the world is in the oceans. And most of the fresh water in the world is inaccessible to us because if it's in ice caps and glaciers, it's in the wrong location and the wrong form as a solid. The water that's easiest for us to use is fresh water that's in lakes or in rivers, and that's just a tiny fraction of the fresh water. But most of the fresh water that's available to us is groundwater that's less than 1 kilometer in depth. So it's a really important resource. And let's watch this video that talks about one of the largest aquifers for agricultural production in the United States, the Ogallala Aquifer. Let me pause the. Okay, so that video is actually from 10 years ago, and I wish I could say that the aquifer was doing way, way better, but it's still highly dependent on rainfall patterns, and so in periods of drought, it falls dramatically. In wet years, it recharges slightly, but it's still down and not where it should be. Part of the reason is if you think about the economic incentives that someone will make money by pumping the water out, but there's no economic incentive now to leave the water in the ground, especially when the next farmer, in the farm next to you may be continuing to take the water because the water can move sideways. In addition to coming up from the ground, it moves sideways to whoever's pumping the most. So there's some really difficult incentives in place that limit the ability of people to solve that problem. This is a side view of an aquifer, and what we say an aquifer is some sort of a geologic formation where the water can be withdrawn. And we distinguish that from an aquiclude, which has water but doesn't really transmit it because the hydraulic conductivity of materials like clay are so low, or an aquafuge, which is something that doesn't have water and also can't transmit it. This is showing the difference between an unconfined aquifer and a confined aquifer. An unconfined aquifer has above it only materials that can easily transmit water. This cross-hatched section here is showing something that's impervious or semi-impervious, and so it could be like a layer of rock or clay that has a really low hydraulic conductivity. Where you've got water above a clay layer, it's unconfined if there's just only the high transmissivity, hydraulic conductivity water above it, soil above it. And then in the confined aquifer, you'll notice that you can have the recharge at a location that's elevated to the aquifer where it causes pressurization. This is an example of an aquifer that's called an artesian well. If the pressure inside of the aquifer is high enough that the water flows up to the surface, then that's defined as an artesian well. And so that can only occur when you've got recharge and confining layers that kind of force the water as though it's through a channel into low-lying areas where it's going to become pressurized. So the main thing that you need to take away from this is that a pressurized aquifer is possible when you have a confining layer at the top and at the bottom. So the confining layer at the top and the bottom makes that a confined aquifer. So artesian is when it's under pressure. An aquitard is any kind of a formation that slows or stops the flow of water. And then a leaky aquifer is one that water is flowing out of the aquifer. So in the case of this confined aquifer, for example, You'll see that water could flow through, like if there's a penetrating well that goes down through the layers, water's going to flow to the surface through the penetrating well. But like if this was partly transmissible, then water could also be seeping upward into the unconfined aquifer because it's pressurized in the confined aquifer. Or if this is a clay layer, it could be that water is leaking downward through that clay layer at a very slow rate, but it could be a leaky aquifer. When we have a well penetrating an aquifer and water is being pumped out of the well, it causes what's known as a cone of depression. So a cone of depression is, in this figure, this horizontal line, the static water table, is where the water surface elevation would be before you start pumping. So if you had a well that you'd turned off, after a couple of days, the water level would just rise to a certain elevation that's reflective of the aquifer in general. But in the proximity of the well, if you turn on pumping, it's going to draw down the water level near the well because the water that's getting pumped out has to be replaced. And so you can see that these arrows are indicating that the water is flowing radially in the direction towards the well, and then it's drawing down the water surface elevation in the proximity to the well because that's what drives the flow towards the well. The water wouldn't flow in the direction of the well to replace the water that had been extracted if there wasn't lower pressure in the vicinity of the well. So let me just jump ahead to an overhead view. This is a picture of Marshall's campus, Buzzkirk Field. So if there was a pump in the middle of Buzzkirk Field that was withdrawing water, then the water would be coming towards the pump from all directions if we were looking at it from above. So in a top view, you can see that the radial flow just means that it's going towards the well, and there's a circular pattern that you could say all of the locations on this circle would be contributing equally if this is a homogeneous soil type. So the cone of depression is just the reduced water surface that occurs when you're withdrawing water from a well. So when we get together on Wednesday, what we're going to do is look at some equations that allow you to calculate what's the flow rate of water that can come out of a well depending on its hydraulic conductivity and as reflected by the amount of drawdown. So we'll get numerical with this and start calculating well equations in class on Wednesday.